From the depths of the ocean to the vast reaches of space, and even some quirky corners of everyday life, these incredible truths are guaranteed to make you question everything you thought you knew.
Saturn, the second largest planet in our solar system, is famous for its stunning ring system, but it has another fascinating characteristic: it could theoretically float in water. This unusual fact stems from the planet's composition and density. Saturn is classified as a gas giant, meaning it is primarily made of gases like hydrogen and helium, with only a small, dense core of heavier elements. Because of this composition, its average density is incredibly low, even lower than water. The average density of Saturn is about 0.687 grams per cubic centimetre, which is significantly less than the density of water, at 1 gram per cubic centimetre. This means that if there were an ocean large enough to hold Saturn, the planet would indeed float, much like an ice cube in a glass of water. However, this is of course a purely hypothetical scenario, since such a vast body of water doesn't exist in the universe as we know it. Saturn's low density highlights the unique nature of gas giants compared to terrestrial planets like Earth. While Earth and other rocky planets have solid surfaces and higher densities due to their composition of metals and silicates, gas giants are primarily composed of lighter elements, which makes them much less dense. Saturn, in particular, has the lowest density of all the planets in the solar system, which is why it holds this peculiar distinction. This characteristic is also a reminder of how different the environments and physical properties of planets can be. The gases that make up Saturn are held together by gravity, and the planet has no solid surface. The density of its atmosphere decreases as you move outward, blending seamlessly into the vacuum of space. This means that if you were to descend into Saturn's atmosphere, you would encounter increasingly dense layers of gas, but you would never find a solid surface to land on. Saturn's ability to float in water is a fun fact that underscores the diversity and wonder of the planets in our solar system. It also helps us understand the physical and chemical properties that define gas giants, offering insight into the formation and structure of these massive planets.
The Moon, Earth's only natural satellite, experiences extreme temperature variations due to the lack of an atmosphere to regulate and distribute heat. On the side facing away from the Sun, commonly referred to as the dark side during nighttime, the surface temperature can plummet to an astonishing -280 degrees Fahrenheit, which is -173 degrees Celsius. This drastic drop occurs because the Moon cannot retain heat once the Sun sets, as it lacks an insulating atmosphere like Earth's. The Moon's temperature extremes are a direct result of its lack of atmosphere. On Earth, our atmosphere acts as a blanket, trapping heat during the day and redistributing it to maintain relatively stable temperatures. The Moon, however, has no such atmospheric layer. Instead, its surface is exposed to the vacuum of space, allowing it to rapidly lose heat through thermal radiation when the Sun is not shining on it. A lunar day lasts about 29.5 Earth days, meaning that one side of the Moon is exposed to sunlight for approximately 2 weeks, followed by 2 weeks of darkness. During the daytime, the surface temperature can soar to around 260 degrees Fahrenheit, or 127 degrees Celsius. But once the Sun sets, the heat quickly dissipates, and the temperature plunges to -280 degrees. These extreme conditions make the Moon one of the harshest environments in the solar system. The Moon's regolith, or surface layer, also plays a role in these temperature fluctuations. Made of fine dust and rocky debris, the regolith has low thermal conductivity, meaning it doesn't store heat well. As a result, the surface cools rapidly once the Sun disappears, while the deeper layers of the regolith remain relatively unaffected by these temperature swings. These extreme temperatures pose significant challenges for lunar exploration and habitation. Spacecraft, instruments, and habitats must be designed to withstand both the searing heat of the lunar day and the frigid cold of the lunar night. For example, the Apollo missions, which sent astronauts to the Moon between 1969 and 1972, required advanced thermal control systems to protect equipment and astronauts from these extreme conditions. The stark temperature difference on the Moon provides insight into how atmospheres play a crucial role in moderating planetary climates. It also highlights the unique challenges of exploring and potentially colonizing worlds without atmospheres. Understanding and adapting to these extremes is vital as humanity sets its sights on returning to the Moon and establishing a long-term presence there through programs like NASA's Artemis mission.
Saturn's North Pole is home to one of the most fascinating and mysterious weather phenomena in the solar system, a giant, hexagon-shaped storm. First discovered by the Voyager spacecraft during their flybys in the early 1980s and later studied in greater detail by NASA's Cassini spacecraft, this massive storm has captivated scientists for decades due to its unusual geometric shape and immense scale. The hexagon is an enormous jet stream encircling Saturn's North Pole, spanning about 20,000 miles or 32,000 kilometers in diameter, large enough to fit 4 Earths across it. Unlike most storms, which tend to be circular or amorphous in shape, this storm's 6-sided symmetry is remarkably precise, making it a unique feature in planetary weather systems. The hexagon rotates counterclockwise, with winds reaching speeds of up to 200 miles per hour or 320 kilometers per hour. Within the hexagon, there is another intriguing feature: a massive, hurricane-like vortex at the very center of Saturn's North Pole. This vortex has a clearly defined eye and towering clouds, resembling hurricanes on Earth, but much larger and more intense. The exact cause of the hexagonal shape is still a subject of scientific investigation, but researchers believe it is related to the dynamics of Saturn's atmosphere. One leading theory suggests that the hexagon is a standing wave pattern created by differences in wind speeds at various latitudes. Laboratory experiments have shown that when fluids are rotated at different speeds, polygonal shapes can form, lending support to this hypothesis. Another factor may be the absence of solid landforms or a substantial atmosphere to disrupt the flow of winds on Saturn, allowing the hexagonal pattern to remain stable over time. Unlike Earth's weather systems, which are influenced by oceans, continents and atmospheric moisture, Saturn's atmosphere is composed mostly of hydrogen and helium, with minimal friction to disturb these large-scale patterns. What makes the hexagon even more remarkable is its apparent longevity. The storm has been observed consistently for more than 40 years, suggesting that it may have been present for centuries or even millennia. This stability is unusual for a storm system, as most storms on Earth dissipate relatively quickly. The hexagon's durability highlights the unique conditions of Saturn's atmosphere, where powerful jet streams can persist for extended periods. Saturn takes about 29.5 Earth years to complete one orbit around the Sun, meaning each season on the planet lasts roughly 7 years. The hexagon becomes more visible during Saturn's spring and summer in the northern hemisphere, as sunlight illuminates the pole, allowing spacecraft and telescopes to observe it in greater detail. During the winter, when the pole is shrouded in darkness, observations become more challenging. The hexagonal storm provides a unique opportunity to study atmospheric dynamics on a gas giant. By understanding how such a phenomenon forms and persists, scientists can gain insights into the behavior of planetary atmospheres both within and beyond our solar system. It also raises questions about whether similar patterns might exist on other gas giants like Jupiter or exoplanets with similar atmospheric compositions. In summary, Saturn's hexagonal storm is not only a visual marvel, but also a scientific enigma. Its geometric perfection, massive scale and persistence make it one of the most intriguing features in the solar system, offering a glimpse into the complex and alien weather systems of a distant world. The Sun, the massive star at the center of our solar system, is constantly losing mass at an astonishing rate of 4 million tons per second. This phenomenon occurs because the Sun is continuously converting its mass into energy through the process of nuclear fusion. This energy powers the sun's light and heat, which sustain life on Earth and govern the dynamics of the entire solar system. How the sun loses mass. At the core of the sun, temperatures reach an incredible 15 million degrees Celsius, or 27 million degrees Fahrenheit, and pressures are unimaginably high. Under these conditions, hydrogen nuclei, or protons, collide and fuse together to form helium. This process, known as nuclear fusion, releases a tremendous amount of energy according to Einstein's famous equation, E equals mc squared. Here, m represents the mass lost during fusion and c the speed of light, amplifies even a small amount of mass into an enormous amount of energy. Each second, approximately 600 million tons of hydrogen are fused into helium in the sun's core. While most of the mass remains in the form of helium, about 4 million tons are converted into energy which radiates outward as sunlight and other forms of electromagnetic radiation. Solar wind contribution. In addition to mass lost through nuclear fusion, the sun loses matter via the solar wind, a stream of charged particles, mostly electrons, protons and helium nuclei, that are ejected from the sun's outer atmosphere, or corona. This stream spreads throughout the solar system, influencing planetary atmospheres and creating phenomena like the auroras on Earth. Although the solar wind accounts for a much smaller mass loss compared to nuclear fusion, it still contributes to the gradual erosion of the sun's total mass, the scale of mass loss. While 4 million tons per second sounds enormous, it's a tiny fraction of the sun's total mass, which is about 2 times 10 to the 30th kilograms, 2 followed by 30 zeros. Over the sun's 4.6 billion year lifetime, it has lost only about 0.03% of its total mass. This means that the sun's mass loss has a negligible impact on its gravitational pull and its ability to sustain the solar system. Despite the sun's immense energy output and mass loss, it is remarkably stable and will continue shining for billions of years. It is currently in the middle of its life cycle, known as the main sequence, where it steadily converts hydrogen into helium. However, as the sun ages, it will eventually exhaust its hydrogen supply, leading to changes in its structure and size. In about 5 billion years, the sun will enter the red giant phase, expanding to engulf the inner planets, including Earth. During this phase, the sun will lose mass more rapidly as it sheds its outer layers into space, forming a planetary nebula. Eventually, it will collapse into a white dwarf, a dense remnant that will no longer undergo nuclear fusion. The sun's mass loss has subtle but measurable effects on the solar system. As the sun loses mass, its gravitational pull weakens slightly, causing the orbits of planets to slowly drift outward. Over billions of years, this will slightly alter the distances between the sun and its planets, though the effect is minimal on human timescales. The sun's constant mass loss is a reminder of the dynamic and ever-changing nature of the universe. It underscores the immense energy production that sustains life on Earth while hinting at the inevitable changes that all stars undergo. This process also highlights the profound relationship between mass and energy, a cornerstone of modern physics. In summary, the sun's loss of 4 million tons of mass every second is a natural and ongoing process driven by nuclear fusion and solar wind. While it has little immediate effect on the solar system, it plays a crucial role in powering the sun and shaping its life cycle over billions of years.
Rogue planets, also known as free-floating planets or nomadic planets, are celestial bodies that wander through space without being gravitationally bound to a star. Unlike planets in solar systems which orbit a central star, rogue planets travel through the galaxy untethered. These enigmatic objects are fascinating to scientists because they challenge traditional definitions of planets and expand our understanding of planetary formation and behavior. What are rogue planets? A rogue planet is essentially a planet that does not orbit a star. Instead, it drifts freely through interstellar space. These planets are thought to be similar in composition to regular planets, ranging in size from small rocky Earth-like worlds to massive gas giants. However, because they lack a nearby star to illuminate them, rogue planets are extremely difficult to detect and study. How do rogue planets form? Scientists believe rogue planets can form in two main ways. First, ejection from a star system. During the early stages of a solar system's formation, gravitational interactions between planets and other massive objects, like stars or gas clouds, can lead to one or more planets being flung out of the system. This violent process, known as planetary ejection, results in planets that roam the galaxy alone. Second, direct formation in isolation. Some rogue planets may form directly in interstellar space, much like stars do. In this scenario, a cloud of gas and dust collapses under its own gravity, but it doesn't gather enough mass to ignite nuclear fusion, which is the process that turns stars into luminous bodies. Detection and challenges. Rogue planets are incredibly difficult to observe because they do not emit light like stars and do not reflect light from a nearby star. Instead, they are often detected using indirect methods. Microlensing. When a rogue planet passes in front of a distant star, its gravity bends and magnifies the star's light in an effect called gravitational microlensing. This allows astronomers to infer the presence of the planet. Infrared observation. Rogue planets may emit faint infrared radiation due to residual heat left over from their formation, which can be picked up by specialized telescopes. In 2021, astronomers discovered a rogue planet candidate in the Milky Way using microlensing techniques. Some estimates suggest there may be billions of rogue planets in our galaxy alone, potentially outnumbering stars. Life on rogue planets? Although rogue planets are cold and dark due to the absence of a nearby star, some scientists speculate that certain types of rogue planets might still harbor life. For instance, a rogue planet with a thick atmosphere and internal heat generated by radioactive decay or tidal forces could sustain liquid water beneath its surface. Similarly, subsurface oceans, like those thought to exist on moons such as Europa and Enceladus in our solar system, could provide environments where life might thrive even in the absence of sunlight. The scientific significance of rogue planets. Studying rogue planets is crucial for understanding planetary formation and the dynamic processes that shape solar systems. These wandering worlds provide clues about the chaotic nature of early solar systems and the mechanisms that lead to planetary ejection. They also offer a unique perspective on the diversity of planets in the universe, as their isolation challenges traditional assumptions about planetary environments. Moreover, rogue planets might act as stepping stones for future space exploration. Their abundance and potential proximity to Earth mean that in the distant future, they could serve as waypoints for interstellar travel or exploration. A mysterious class of objects, rogue planets blur the lines between planets, brown dwarfs, objects too large to be planets but too small to sustain nuclear fusion like stars, and other celestial bodies. Some scientists argue that rogue planets with star-like characteristics should be classified differently, adding complexity to the debate over how we define planets. In summary, rogue planets are mysterious and awe-inspiring objects that challenge our understanding of planetary science. Their existence reveals the dynamic and often chaotic nature of the universe, offering a glimpse into worlds unbound by the gravitational pull of a star. As detection methods improve, we may uncover more of these wandering worlds and learn even more about their origins, characteristics, and potential for hosting life.
Jupiter, the largest planet in our solar system, is not only known for its immense size and iconic Great Red Spot, but also for its extraordinary number of moons. As of 2024, astronomers have confirmed that Jupiter has 92 moons, making it the planet with the most natural satellites in the solar system, surpassing even Saturn, which has 83 confirmed moons. These moons range in size, composition, and characteristics, providing a fascinating glimpse into the diversity of celestial objects orbiting a giant planet. Jupiter's four largest and most well-known moons, Io, Europa, Ganymede, and Callisto, are called the Galilean moons, named after the astronomer Galileo Galilei, who discovered them in 1610. These moons are some of the most studied objects in the solar system due to their unique features. Io, the most volcanically active body in the solar system, has a surface constantly reshaped by massive eruptions caused by tidal forces from Jupiter's gravity. Europa, beneath its icy crust, is believed to harbour a vast subsurface ocean, making it a prime candidate in the search for extraterrestrial life. Ganymede, the largest moon in the solar system, is even bigger than the planet Mercury and is the only moon known to have its own magnetic field. Callisto, a heavily cratered ancient moon, has a surface that is one of the oldest in the solar system, preserving a record of impacts over billions of years. Beyond the Galilean moons, Jupiter has dozens of smaller satellites that vary greatly in size and composition. These moons are generally divided into two categories: regular moons and irregular moons. Regular moons have nearly circular orbits and lie close to Jupiter's equatorial plane. They likely formed from the same disk of gas and dust that created Jupiter. Examples include Amalthea, Thebe, Adrastea, and Metis, which are relatively small compared to the Galilean moons. Irregular moons are captured objects, likely asteroids or comets, that were gravitationally snagged by Jupiter. They have highly elliptical, inclined, and sometimes retrograde orbits, meaning they orbit in the opposite direction of Jupiter's rotation. Most of Jupiter's moons fall into this category, with clusters named after their orbital characteristics, such as the Himalaya group or Ananke group. The tally of Jupiter's moons has steadily increased over the years thanks to advancements in telescope technology and observation techniques. Many of the newly discovered moons are tiny, with diameters of just 1 to 3 kilometers, making them difficult to detect. These discoveries often involve large-scale surveys using ground-based telescopes equipped with sensitive cameras, such as those conducted in Hawaii or Chile. In early 2023, astronomers announced the discovery of 12 additional moons, bringing Jupiter's total to 92. These discoveries highlight the dynamic nature of planetary science as new moons are continuously being identified and confirmed. Jupiter's massive size and strong gravitational pull make it a natural collector of moons. Its gravity allows it to capture objects that stray too close, such as asteroids and comets. Additionally, during its formation, Jupiter had a massive disk of gas and dust surrounding it, from which some of its moons coalesced. This combination of capture and co-formation processes has led to Jupiter's impressive collection of moons. Studying Jupiter's moons provides valuable insights into the formation and evolution of the solar system. The Galilean moons, in particular, are like mini-worlds with diverse geological and atmospheric processes. Europa, with its potential subsurface ocean, is of great interest in the search for extraterrestrial life, while Io offers a window into extreme volcanic activity. Additionally, the irregular moons offer clues about Jupiter's gravitational influence and the population of objects in the outer solar system. These moons may include ancient remnants of the early solar system, preserved in their current orbits for billions of years. Several missions are focused on studying Jupiter and its moons. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, has provided detailed data about the planet and its environment, including close flybys of some of its moons. The upcoming Europa Clipper mission, set to launch in the 2020s, will specifically investigate Europa's habitability. Additionally, the European Space Agency's JUICE, or Jupiter Icy Moons Explorer mission, launching in 2023, aims to study Ganymede, Callisto, and Europa in detail. Jupiter's 92 moons showcase the planet's gravitational dominance and its role as a miniature solar system within our larger solar system. From the volcanic hellscape of Io to the icy oceans of Europa, these moons offer a wealth of scientific opportunities. As technology improves and future missions explore these fascinating worlds, Jupiter's moons will continue to provide key insights into the mysteries of the cosmos.
Mars, the fourth planet from the Sun, is a fascinating world with many peculiarities, and one of its most mesmerizing features is its blue sunsets. Unlike Earth, where sunsets appear warm hues of orange, pink and red, Martian sunsets take on an ethereal blue tint, providing a striking visual contrast to the planet's dusty, red-hued landscape. The unique coloration of Martian sunsets is caused by the interaction between sunlight and the fine dust particles that dominate Mars' thin atmosphere. On Earth, sunsets appear red or orange due to a phenomenon called Rayleigh scattering, where shorter wavelengths of light, blue and violet, are scattered by atmospheric molecules, leaving the longer wavelengths, red and orange, to dominate. Mars, however, experiences a different type of scattering known as Me scattering, caused by the fine, iron-rich dust particles suspended in its atmosphere. These particles are just the right size to scatter blue light more efficiently than other colours. During sunset, when sunlight passes through a longer column of the Martian atmosphere, the blue light is scattered forward, concentrating it in the direction of the Sun. This effect makes the Sun and the area around it appear bluish, creating the iconic Martian blue sunset. Mars's atmosphere is incredibly thin, about 1% the density of Earth's, and is composed mostly of carbon dioxide, 95%. Despite its thinness, it is filled with fine dust particles, many of which are lifted into the atmosphere by frequent dust storms. This omnipresent dust plays a crucial role in shaping the colour and appearance of the Martian sky. Interestingly, during the day the Martian sky appears a pale butterscotch or yellowish red, largely due to sunlight scattering off the iron oxide-rich dust that gives Mars its nickname, the Red Planet. However, during sunset the concentration of scattered blue light becomes pronounced, creating the stunning contrast. Mars's blue sunsets were first captured by robotic missions exploring the planet, such as NASA's Spirit, Opportunity, Curiosity and Perseverance rovers. These rovers provided photographic evidence of the phenomenon, which matches scientists' predictions about the scattering effects in the Martian atmosphere. For example, NASA's Curiosity rover, which has been exploring Mars since 2012, captured some of the most detailed images of these blue sunsets from Gale Crater. The images show how the Sun dips below the horizon, surrounded by a glowing bluish halo. The Martian blue sunset highlights the intricate interplay between light and the environment. On Earth, our atmosphere scatters blue light across the sky, giving it its characteristic colour during the day. On Mars, the situation is reversed. Blue is more prominent at sunset due to the specific size, composition and behaviour of dust particles in the thin atmosphere. This difference also underscores how unique each planetary environment is. The optical phenomena we take for granted on Earth, like sunsets, can look dramatically different elsewhere in the solar system, influenced by factors such as atmospheric composition, pressure and particle size. The blue sunsets of Mars have become a symbol of the alien beauty of the Red Planet and a source of inspiration for scientists and dreamers alike. They remind us that even in environments vastly different from our own, there are moments of profound beauty. These sunsets offer a glimpse of what it might be like for future astronauts to stand on the Martian surface, witnessing a sky that is at once familiar and utterly alien. Conclusion. Mars's blue sunsets are a striking example of how the interplay of light and atmospheric conditions can produce phenomena that are both scientifically fascinating and visually stunning. They serve as a reminder of the unique characteristics of other worlds and the importance of exploring and understanding the vast diversity of the universe. From the pale blue dot of Earth to the blue-tinted sunsets on Mars, our solar system is full of wonders waiting to be uncovered.
The phenomenon of a star being stretched into spaghetti if it passes too close to a black hole is a dramatic and scientifically fascinating process known as spaghettification or tidal disruption. This effect highlights the immense gravitational forces that black holes exert on their surroundings and provides a glimpse into the extreme environments near these cosmic giants. What is spaghettification? Spaghettification refers to the extreme stretching and elongation of an object, such as a star, caused by the intense tidal forces near a black hole. Black holes have incredibly strong gravitational fields due to their massive density. As an object approaches the black hole, the gravitational pull it experiences varies significantly across its length. The side of the object closer to the black hole feels a much stronger gravitational force than the far side, creating a tidal effect. If a star ventures too close to the black hole's event horizon, the boundary beyond which nothing can escape, these tidal forces become so intense that the star is stretched into a thin, elongated shape resembling spaghetti. This process can tear the star apart entirely, breaking it into streams of stellar material. The intensity of tidal forces depends on the mass of the black hole and the distance of the star from it. Smaller black holes with masses comparable to a few times that of the Sun have stronger tidal forces near their event horizons, making spaghettification likely even before an object crosses the event horizon. Larger black holes, such as supermassive black holes found at the centers of galaxies, have weaker tidal forces near their event horizons, allowing objects to approach closer before experiencing spaghettification. When the star gets too close to the black hole, the side facing the black hole is pulled more strongly, stretching the star along the direction of gravity. The star is simultaneously compressed along its width due to gravitational forces acting perpendicularly, resulting in a long, thin stream of material. Eventually, the star's material is torn apart and forms an elongated stream of gas. The destruction of a star by a black hole, known as a tidal disruption event, or TDE, is a rare but spectacular cosmic event. As the star's material spirals into the black hole, it forms an accretion disk, a swirling disk of superheated gas and dust. The process generates immense energy, producing bright flares of electromagnetic radiation, including X-rays, ultraviolet, and visible light. These flares are detectable by astronomers and provide valuable information about black holes and the extreme physics governing them. In 2020, astronomers observed a notable TDE named at 2019 Keyes, which occurred about 215 million light-years away in the constellation Eridanus. This event gave scientists one of the clearest views of a star being torn apart by a black hole. The likelihood and nature of spaghettification depend on the mass of the black hole. Stellar mass black holes. These smaller black holes, formed from the collapse of massive stars, have more intense tidal forces near their event horizons. A star encountering such a black hole would be shredded and stretched far before it even reaches the event horizon. Supermassive black holes. These giants, with masses millions to billions of times that of the Sun, have weaker tidal forces near their event horizons. A star can approach much closer before being torn apart. In some cases, the star may partially survive the encounter, with only some of its material being accreted. Spaghettification and TDEs offer astronomers a rare opportunity to study black holes indirectly. Since black holes themselves emit no light, observing the bright flares caused by TDEs allows scientists to learn about the mass and spin of black holes, the behavior of matter under extreme gravitational forces, and the processes governing accretion disks and energy generation near black holes. These events also help confirm predictions made by Einstein's general theory of relativity, particularly regarding the effects of extreme gravity on matter and light. The spaghettification of a star serves as a striking reminder of the immense power of black holes, the most extreme objects in the universe. It showcases how gravity, one of the fundamental forces of nature, can dominate and shape the behavior of matter on an astronomical scale. For a star, an encounter with a black hole marks its ultimate demise, but for astronomers, it illuminates some of the deepest mysteries of the cosmos. Spaghettification is a dramatic and fascinating phenomenon that exemplifies the incredible forces at play near black holes. While terrifying in its implications, it provides invaluable insights into the workings of the universe and the extreme conditions that define black hole environments. Each tidal disruption event observed offers a rare chance to study these enigmatic cosmic monsters, advancing our understanding of space, time, and gravity.
Alpha Centauri, the closest star system to Earth, is a fascinating and complex celestial neighbour. Situated just over 4.37 light-years away from our solar system, It is a three-star system consisting of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Despite its proximity in cosmic terms, the distance underscores the vast scale of interstellar space, as light traveling at 186,000 miles per second takes over 4 years to reach us from this system. The Alpha Centauri system consists of 3 distinct stars, Alpha Centauri A and B. These 2 stars form a binary pair orbiting each other in a shared gravitational dance. Alpha Centauri A is a G-type star similar to our Sun, slightly larger and brighter. Alpha Centauri B is a K-type star slightly smaller and cooler than the Sun. They orbit each other at an average distance of about 11 astronomical units, roughly the same distance as Saturn is from the Sun. Proxima Centauri. This is the smallest and faintest of the 3 stars. It is a red dwarf star located about 0.22 light-years from Alpha Centauri A and B. Proxima Centauri is the closest individual star to Earth at a distance of 4.24 light-years. Proxima Centauri is particularly intriguing because it has at least 2 known planets, Proxima b, a rocky exoplanet located in the star's habitable zone, where temperatures might allow for liquid water to exist on its surface. Proxima b is only slightly larger than Earth and has sparked considerable interest as a potential location for extraterrestrial life. Proxima c, a larger, possibly gaseous planet with a much wider orbit, making it unlikely to support life as we know it. Proxima Centauri is a flare star, meaning it experiences sudden and intense bursts of radiation. These stellar flares could pose challenges for life on any planets within its system, as they might strip away atmospheres or irradiate the surface. Challenges of interstellar travel. Despite being the closest star system, traveling to Alpha Centauri is a daunting challenge due to the immense distances involved. At current spacecraft speeds, it would take tens of thousands of years to reach the system. For example, NASA's Voyager 1, traveling at about 38,000 miles per hour, would take over 70,000 years to reach Alpha Centauri. Proposed technologies like the Breakthrough Starshot project aim to send tiny laser-propelled spacecraft to Alpha Centauri at a significant fraction of the speed of light, potentially reducing travel time to just a few decades. Scientific importance of Alpha Centauri. Alpha Centauri holds a special place in the search for life and understanding of planetary systems. Its proximity makes it a prime target for telescopes and future interstellar missions. Scientists hope to study Proxima b and other potential planets for signs of habitability. They also aim to observe the system's dynamics to better understand the formation and evolution of planetary systems. The James Webb Space Telescope, along with other upcoming observatories, may provide more detailed information about the atmospheres and compositions of planets in the Alpha Centauri system. Cultural significance. Alpha Centauri has long captured the human imagination, serving as a backdrop for countless works of science fiction. It represents the closest step on humanity's journey toward exploring the galaxy and symbolizes the vastness and possibilities of the cosmos. In stories and scientific discussions, it often serves as humanity's first destination for interstellar exploration. Conclusion. Alpha Centauri, though just over 4 light-years away, remains tantalizingly out of reach for current space travel capabilities. Its 3-star system, with the promise of potentially habitable planets like Proxima b, continues to inspire astronomers and the public alike. As technology advances, Alpha Centauri will likely play a central role in humanity's quest to reach the stars and uncover the mysteries of the universe.
The International Space Station, humanity's largest and most advanced orbital laboratory, travels at an astounding speed of 5 miles per second, which is approximately 28,000 kilometers per hour or 17,500 miles per hour. This incredible velocity enables the ISS to orbit Earth about once every 90 minutes, allowing its crew to witness 16 sunrises and sunsets every day. The station's rapid speed is crucial for maintaining its orbit and countering the gravitational pull of Earth. The high speed of the ISS is a result of the delicate balance required to maintain orbit around Earth. The ISS is essentially in a state of free fall, continuously falling toward the planet, but moving forward so quickly that it keeps missing the surface. This phenomenon is known as orbital motion. At an altitude of approximately 400 kilometers or 250 miles above Earth's surface, the ISS must travel at this speed to generate sufficient centrifugal force to counteract Earth's gravitational pull. If the ISS were to slow down, it would descend and eventually burn up in the atmosphere. Conversely, if it traveled too fast, it would escape Earth's gravity altogether. The speed of the ISS is governed by the principles of orbital mechanics, specifically Newton's laws of motion and the law of universal gravitation. To stay in a stable low Earth orbit, the ISS must maintain a precise balance between its velocity and the gravitational force acting on it. Gravitational force pulls the ISS toward Earth, while forward velocity ensures that the ISS moves along a curved trajectory, effectively falling around the planet rather than into it. This balance allows the ISS to orbit Earth without the need for continuous propulsion, relying instead on its momentum and occasional adjustments by on-board thrusters to counteract minor drag from the upper atmosphere. Living and working on the ISS at such high speeds is an extraordinary experience for astronauts. From their perspective inside the station, they do not feel the speed because everything around them is moving at the same velocity. However, the effects of the rapid orbit are evident: multiple sunrises and sunsets. The crew experiences a complete day-night cycle every 90 minutes, which can disrupt circadian rhythms. To counter this, astronauts follow a carefully planned schedule based on Coordinated Universal Time, or UTC, rapid travel around the globe. The ISS crosses continents and oceans in mere minutes, allowing astronauts to observe geographical and meteorological phenomena on a global scale. The station's incredible speed also enables it to serve as a unique platform for scientific research, offering opportunities to study microgravity, Earth's atmosphere, and cosmic phenomena in real time. While the ISS's velocity is essential for maintaining orbit, it also presents challenges. Debris hazards. Even small pieces of space debris, traveling at comparable speeds, pose significant risks. The kinetic energy of an object increases exponentially with speed, making even a paint chip potentially destructive. To mitigate this, the ISS is equipped with protective shielding and can perform collision avoidance maneuvers to evade larger debris. Atmospheric drag. Although the ISS orbits above most of Earth's atmosphere, it encounters trace amounts of air particles that create drag and gradually lower its altitude. Periodic reboosts using thrusters or visiting spacecraft help maintain its orbit. The ISS's incredible speed means it crosses the sky in just a few minutes, appearing as a bright, fast-moving point of light. Enthusiasts can track its location using apps or websites to observe it during favorable passes. Its speed and orbit make it one of the most easily visible artificial objects in the night sky. The ISS's rapid speed is not just a technical necessity. It is also symbolic of the cutting-edge collaboration and innovation that the station represents. As an international partnership between agencies like NASA, Roscosmos, ESA, JAXA and CSA, the ISS has become a hub for scientific discovery, technological development and global cooperation. Its velocity reflects humanity's determination to explore and push the boundaries of what is possible in space. Conclusion. Travelling at 5 miles per second, the International Space Station is a marvel of human engineering and scientific achievement. Its speed is essential for maintaining orbit and enables it to serve as a unique platform for research and discovery. Despite the challenges posed by its velocity, the ISS continues to provide invaluable insights into life in space and the universe beyond, inspiring humanity's journey into the cosmos.
Thank you for watching. We hope these mind-blowing facts left you amazed and inspired. Don't forget to like, subscribe and hit that notification bell because there's plenty more where that came from. Stay curious and we'll see you in the next one.